Hi, I Aziz, welcome to your CoedMaster, and in this video I am going to talk about omega notation. So let's get started. So let's say we are given a function to solve a problem, and we are also given expression of time taken by this program to solve a problem. Now we have to find the order of growth of this function. Here we can use direct method of asymptotic analysis to find the order of growth of this function or an algorithm. How we do it? The direct method says cancel the lower order term, cancel the coefficient of higher order term, and then you get the final order of growth of a function. So here 2 is the lower order term, so we cancel out the 2. So our most dominant and higher growing term is n, and 3 is the coefficient of this n. So we remove this 3 also, and we finally get the n. So we could say that the order of growth of function n is omega of n. And what omega tells about the algorithm? It tells about the lower bound of an algorithm. It means this algorithm or this program takes at least n unit of time to solve a problem. It may also take more than n. Let's say for example n square, n cube. But omega notation especially tell about the lower bound of the order of growth of a function. In this video we are going to talk about the mathematical proof of the omega notation. So let's see. We have a function and the expression of time taken, that is 3n plus 2. We have proved by direct method that order of growth of this function is big O of n. Now what is n here? N is an expression of lower bound, right? So in terms of function we can write like this, g of n is n. So if we put the value of n in this statement, we get the f of n is equal to big omega of gn. Now mathematically this statement is going to be true only if there exists a positive constant n naught and c where c is greater than 0 and n naught is greater than 0, such that c dot gn is less than fn for all n greater than 0. So what does it mean? That we can say that f of n is big omega of gn only if this statement satisfies. So basically we need to find the value of c and the g. So let's see with an example. So we have function and the time taken by this function is 3n plus 2 and we have gn. Now in this equation let's substitute the value of gn and fn. So when we substitute the value of g and fn, we get this statement, c dot n less than equal to 3n plus 2. Now we need to choose a value of c such that this expression is going to be smaller than this expression. So we need a value of c. So here we are taking value of c as 1. Why? Because the highest growing term is n and the coefficient of n is 3. So we are taking just 2 less than this number. In big O notation, we are taking the higher number because we are talking about upper bound. But in omega, we always talk about the lower bound. That's why I am taking 2 number less than this number, and that is 1. So if we put the value of c is equal to 1, then we get 1n is less than equal to 3 into n plus 2. Now it becomes minus 2 is less than equal to 2n, and we cancel out 2 by 2. It becomes n is greater than minus 1. So for all the values of n greater than equal to minus 1, this statement is going to be satisfied. And if this statement is going to be satisfied, then only we can say that f of n is big omega of gn. So what would be our n naught then? So if all the values of n greater than minus n satisfy this condition, then obviously n greater than 0 is also going to satisfy this condition. And as we talk about only the positive values, so we consider only positive values here. So we just ignore the negative values. So let's prove this. Let's again put the value of c and n naught in the statement and prove that statement. So we got our value of c as 1, n naught as 0. And when we put this value of c and n naught in this statement, we get 1 dot gn less than 3n plus 2. We substitute the value of c, gn and function. So we get 0 is less than 2. It means we have satisfied this statement because 0 is less than equal to 2. So initially we proved by the direct method that f of n is omega of n. It means it is a lower bound. It means minimum it takes the n unit of time to solve a problem, or it can take more than n. So omega represents the lower bound of a function. So similarly, we have proved mathematically that f of n is big omega of gn. So far so clear. Now the question is where to use omega notation. So let's understand this with an example. Let's say we are given a problem to print the values of array in ascending orders. Okay, so there is going to be two scenarios here. Either we pass array in sorted order, or we can pass array in unsorted order. If I pass sorted array in this function, then the order of growth of this function is going to be n. Why? Because let's say you have 10 values in an array. So you are going to run a loop to print all the values of array. So let's say you have n size array, then you are going to take n unit of time to print the array. On the other hand, let's say if I pass unsorted array instead of sorted array, then I have to do some work, and that work will be to sort the array. So first I sort the array, then I print the array. So the order of growth in this case is going to be n square. So if I ask about the order of growth of this function, then you can say that the order of growth of this function is going to be omega n. Why? Because at minimum this function is going to take n unit of time. The order of growth is n, and it's a lower bound. It may also take more than n. It means n square. If the array is not sorted, it may take n square also. So I hope now you have a clear understanding about omega notation and where to use omega notation. Thanks for watching. See you in the next video.